Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have discussed the Nyquist pulse and the Nyquist filter, by virtue of which, given a bandwidth W, one should be able to send 2 W symbols per second, which produces the maximum symbol packing which is possible. If we consider k bits per symbol, that means if we are doing PAM with k equals to log base 2 of m, in that case we would be getting 2k symbols per second per hertz. That is the maximum limit that one can achieve. So, we revisit that the Nyquist pulse is one whose pulse shape can be represented by a sinc function multiplied by other time functions, and we just explained in the previous lecture that if we consider this as the sinc, suppose I consider, roughly speaking, a sinc goes like this, and I consider another time function, let us say this. So, when I multiply these two, it is going to follow the 0 crossing at appropriate 0 crossing instants, you can't help it. So, this with multiplied by this is generally going to produce this. If you are producing, if you are using some other pulse shape, let us say this, in that case also you are going to get a product of this. So, at 0 crossings this will turn to be zeros, because multiplication of 0 with this is going to produce a 0. So, we might get some shape which we do not know, maybe which we have to calculate, right. So, in the frequency domain what happens? It is a convolution of this produces in the frequency domain a rectangular pulse, and this will produce some frequency domain structure. So, time domain multiplication would mean frequency domain convolution, right. So, that is why we said it is convolution in the frequency domain. So, amongst the class of Nyquist filters, so when we say the class of Nyquist filters, what we mean is all those filters for which the frequency response is convolution of the Nyquist frequency response convolved with any other frequency response of a choice, which would mean if I look at the time domain, the Nyquist pulse multiplied by the pulse of that particular new pulse shape which I am concerned with. This way we are going to produce 0 ISI at the sampling instance of time, which is our desire. So, amongst these several possible things, the raised cosine and the root raised cosine are the most popular. So, we are going to take a look at the raised cosine pulse shape. So, from this picture it is just to remind us what is happening to ensure 0 ISI, and for this particular spectrum we know that the pulse shape would be this, which has an infinite tail as we have just mentioned. Since it is not realizable, we should look for other solutions. Further, we can also note that if we have a pulse shape, a strain of pulses arriving in this manner, so we could redraw for a sketch and trying to understand what goes on. So, if we say that there is a 0 crossing here, right. So, roughly speaking we have done that, and suppose our line goes here. So, we are supposed to sample at this location, at this location, roughly at this location, where this also goes through 0. Now, if the receiver clock makes an error and instead of sampling there, it samples at a little bit offset point. So, if it starts sampling at a little bit offset point, what we see that the desired signal has a lower value, while there is contribution of other symbols from the neighborhood, and we do get a lot of inter symbol interference. So, this although produces orthogonal and the highest packing, but still it has some problems which we can visualize from a situation as depicted here. So, small synchronization errors can cause large interference because of the pulse shape. So, the Nyquist filter, as said, it maximizes the packing, but it is sensitive to clock errors and it has infinite tail. So, although there is an advantage, these are some of the disadvantages. So, we would want to design a pulse with lower tail amplitude. So, if the tail amplitudes are lower, that means if it rises slowly, that means instead of rising there, if the rise would have been like this, if the fall would have been like this, then the amount of interference would have been less, right. We could have produced a lesser amount of interference if the thicker lines would be produced. So, we are looking for a pulse, that means we are looking for pulses with faster decay. So, there the decay is not so fast. The Nyquist characterizes 0 ISI at sampling time. So, we must ensure this, we cannot afford to change this, and the solution, one of the famous solutions is raised cosine, which provides us with the features that we are looking for, right. It will have the Nyquist property as well as the tails are going to die out much faster. Such a filter's channel transfer function is described, it is given. So, we will take it to be given out of design, which is equal to 1 for a certain duration of frequency. We are going to explain these terms shortly. So, it is flat over a certain duration of frequency, and it is equal to cos squared pi by 4 and these expressions for another range of frequencies, right. We are going to depict the picture of this spectrum and things will be clearer, and it is 0 outside W, where W is our spectrum that is available to us. So, where in this particular expression we have W is the absolute bandwidth and W 0 is 1 over 2 t, that is the minimum Nyquist bandwidth required by the spectrum or the minimum Nyquist spectrum. So, what it means is that if I am signaling, if my symbol duration is t, the Nyquist bandwidth is W 0, but I use a practical bandwidth which is W, right. So, in these expressions W 0 to be used is 1 upon 2 t and W is something which is given, and W minus W 0, this particular value is the excess bandwidth factor, that is the additional beyond Nyquist, and the ratio W minus W 0 upon W 0 is defined as the roll off factor. So, this is a parameter. In some cases you might find this particular expression and these frequency relationships are given in terms of roll off factor, which you can also translate by bringing R into the expression by using this relationship. So, W 0, so if W 0 is given, that is the Nyquist bandwidth given, R provides the excess bandwidth as a fraction of W 0, which you can clearly see. If I give W 0, that means if t is given, the symbol duration is given, then we can, and R is given some fraction, then we can calculate what is the excess amount of bandwidth that is required. So, W is equal to R times W per W 0. So, from this you can see W is equal to W 0 into 1 plus R. So, this is R is W is greater than R. So, R is greater than 0, greater than or equal to 0. So, that means W is greater than W 0. So, what we are trying to say before we get into further discussions is, since this is not realizable, we give an excess bandwidth and then we would ask the filter to taper off slowly. So, if we can ask the filter to taper off slowly, this makes a more realizable filter, because a filter with rectangular transfer function is not realizable for all reasons. So, if we can design a better filter with tails which die out faster, we can truncate the tails at a certain point, then in the frequency response we are going to get something like this. So, what is this excess ratio? If we can specify, given this we can find the amount of W that is required. So, all this given a value of symbol duration, that is a symbol rate. So, why do we go in this manner? Because generally you will be given the bits per second to be transmitted, bits per second per hertz is what we calculate. So, if you are given bits per second, you know the modulation, that means you know k, all you are left with is to determine t. So, if you determine t, you get the symbols per second. So, once we get symbols per second, what you can calculate is the Nyquist bandwidth. Now, once you calculate Nyquist bandwidth and you know that Nyquist filters are not realizable, you can allow an excess bandwidth with a certain roll off in the frequency domain, which is more realizable, and you can calculate the overall W that is required. So, that is what is being described by these expressions here. So, the channel impulse response, how do we obtain? Simply by taking the Fourier transform or the inverse Fourier transform of C of f. So, if we take the inverse Fourier transform of this, we will be left with the impulse response, which appears, the expression if you derive would get to something like this. We can't help but use this expression, because there is no point in doing the inverse Fourier transform, which we are supposed to do by ourselves. So, this has tails which go to 0 at sampling instance regardless of the roll off, that we have already said, because we are multiplying with the sink, as you can clearly see. So, if this goes to 0 at sampling, whatever is there will go to 0. Tails fall off as W squared, what you can see in the denominator there is W squared. So, tails would fall off, the power falls off at W to the power 4, and still there is infinite tail, but since it diminishes faster, you can do some truncation, as we have pointed out. So, we will just take a look at how the things look like. So, what we have here, well, we will compare the transfer function and yes, we compare the transfer function and the impulse response in this particular figure. So, what we see is, if I bring to the center, that if we have the roll off factor of 0, we get the rectangular ideal Nyquist filter. Now, this is also possible to understand by looking at this expression. So, if we make R equals to 0, W is equal to W 0, which is the ideal Nyquist bandwidth, and if we let R equals to 1, if R is equal to 1, W is equal to 2 times W 0. So, when R is equal to 1, that is this dashed line, we see that it is a much more relaxed roll off for the filter, right. The pass band has sufficient space. So, you can design a good filter with this, easy filter with this. So, it is spread in the bandwidth, right. And if we look at the corresponding pulse shape, this solid line is for the one where R is equal to 0, that is corresponding to the rectangular pulse shape, right. And if we look at R equals to 1, is the one which is here. So, what we clearly see that if I make the total available bandwidth as twice, I can design a filter with very fast decaying tails. Anything in between 0 and 1, anything in between 0 and 1 would appear like this, and here it is drawn for R is equal to half, which requires 50% excess bandwidth, and the pulse tail goes like this, right. So, what we see, by choosing an appropriate value of R, one can design a suitable pulse, and there would be a corresponding implication on the spectrum that is occupied. Now, what you get is much more realizable situation. However, what you pay is excess bandwidth, which is not required for communication, but you need it for practical realization. So, if you could realize a filter which is very close to the Nyquist, then you have a better communication system. But because of practical constraint, you would set a value of R which is not equal to 0. Neither would you choose R is equal to 1. So, you generally choose somewhere in between 0.5, 0.3 and some things like that, which would give you a good roll off factor and a trade off between the bandwidth efficiency and realizability of the filter. So, what we have is that the raised cosine filter is also not realizable in a strict sense, simply because the tails stretch to infinity. So, if you have such a situation, we would like to design a pulse with a desired roll off and a realizable FIR. So, a more general expression of W with respect to R s is given through R, where we find that Rs by 2 is the W, because if Rs is the signaling rate, the bandwidth required is Rs by 2. So, now through this relationship you can calculate, given a symbol rate, that means if k is specified, that means k bits per second if it is specified, this, and you have k which is specified. So, you could calculate T if you know R, right. That is the reverse way of doing things. That means, I want to calculate the amount of bandwidth that is required given a certain bit rate and a roll-off factor. So, I must be choosing my modulation level, right, and given R, right, I would be able to calculate, because if modulation level is fixed, k upon T should be equal to Rs, that is fixed, I would be able to calculate W. Or in a reverse manner, if W is given, R is given, that means the bandwidth and the roll-off factor, you would be able to calculate what is the symbols per second that you can send. And once you calculate the symbols per second, you have T with you. So, if you have T with you, now you can adjust the value of k if you want to achieve a certain bits per second data rate. So, if you are confined with a certain symbol rate, by increasing k, you can increase the bits per second. So, what we have is, if R is equal to 0, we have the Nyquist situation. If R is equal to 1, you have W is equal to Rs, and R is equal to 0, R is greater than 0 is the bandwidth expansion factor, which is beyond the Nyquist minimum. So, if we look at the raised cosine frequency transfer function, it is composite of the transmit filter, the channel and the receive filter. Why we say this? Because we have stated that we want to have this kind of a received pulse train. Whatever happens, if you receive this, if you get this, there is no ISI, right. If you are sampling at the right points, there is no ISI. So, this is the composite, we want to have the raised cosine. So, if you want to have composite as the raised cosine, you have the transmit filter at the transmitter side, you have the channel, there is a filter, and there is a received filter, right. Generally, the channel is not known a priori, and it has to be estimated and compensated at the receiver, which we will see shortly. So, in those cases, the transmit and receive filter together should give the raised cosine. Of course, we will see there is a equalizer which is present here together, which should give an ideal transfer function. So, under those conditions, if the raised cosine has to be split between the transmit and the receiver, you get a root raised cosine, because when it is root raised cosine, when multiplied in the frequency domain, because you have the filters in sequence cascaded. So, the overall composite transfer function is the multiplication of all this. In the time domain, it is the convolution of all the pulse shapes. So, what we have is the root raised cosine. So, if it is the raised cosine overall, square root when multiplied together in the frequency domain as a transfer function, we get the raised cosine pulse shape. So, that is what we generally do. So, what we see from what we have discussed till now is, as we increase the roll-off factor, right, as we increase the roll-off factor, the W becomes larger, we get a excess bandwidth, right. R is the fraction of excess bandwidth. Our bandwidth efficiency decreases, this is what we have already stated. Whereas, in the reverse way, if I reduce this, bandwidth efficiency increases, but it is more prone to ISI, and here it is easier to do the receiver processing, and it is less prone to ISI. So, these are some of the trade offs which we are usually concerned with. So, as an example, if you take 4 PAM and R is equal to 2.4 kilo bits per second for 100% excess bandwidth, that means R is equal to 1, you are going to get Rs is equal to R by 2, because there are 2 bits per level, So, you have RS by 2. So, you have 1.2 kilo symbols per second. So, bits per second converted to symbols per second, and the bandwidth minimum that is required is half 1 plus RRS. R is 1 because it says 100% excess bandwidth available. You can use 1.2 kilohertz to communicate 2.4 kilobits per second. That is what we get over here. So, in case of voice telephony, if you would extend the example to a voice telephony, the bandwidth of voice typically is 3 kilohertz. So, if we are doing analog communication, we will be requiring to send the signal over a bandwidth which is slightly more than 3 kilohertz. If we do digital communication, we will first sample it and convert to sample sequences at 8 kilohertz per second, because more than twice is 6, which is 8. Each sample, if it is encoded into 8 bits per second, we have 64 kilobits per second without any compression. So, if BPSK is used, that means if we use binary PAM, then each bit is going to take a waveform and we will be using 64 kilo symbols per second, straight ahead 1 bit per symbol. If R is equal to 1, that means roll-off factor is 1, you are going to use 64 kilohertz by the calculations. If instead of using BPSK we go for QPSK, what we get, and we use R is equal to half, we have 24 kilohertz. So, the question that I would like to ask you or keep pondering over, that whether transferring 3 kilohertz voice using analog communication is better than digital communications. So, why I ask this question? Because as you can clearly see, even after using R half and higher order modulation, we still require 24 kilohertz, whereas in case of analog signaling, you would not require more than, let us say, 4 kilohertz at most, or maybe 5 kilohertz. So, this is spectrally much less efficient in terms of message compared to analog, at least in this pseudo example. So, whether it makes sense or not to use digital communication is something we should start thinking. However, I would just like to give it as an exercise for you to think and discuss amongst your friends and come up with the right answer. Just a note, a hint, here we have said no compression. So, to find the answer, think of all possible advantages that a digital communication system gives compared to analog communication system, and the answer will be clear to you. So, with this we come to the next important kind of signaling, where we will address some of the issues that we have discussed so far. So, one of the primary things that we have discussed is that if we are using the maximum signal packing, then we could use Nyquist filters. Nyquist filters are not realizable because the spectrum is rectangular, which is ideal. It produces a sync pulse with large tails, and that causes a non-causal system. So, a better situation is if you could use a little bit of excess bandwidth, provide a little bit of roll off in the filter transfer function instead of rectangular, and then you would get pulse trains with smaller tails. So, if you get pulse trains with smaller tails, then it dies out faster and you could truncate it at a certain point and you could realize the transmission system. But the penalty that is paid is in terms of excess bandwidth, because you have used more than Nyquist and hence your spectral efficiency is reduced. So, the question which you can ask is it possible to communicate at 2W symbols per second when the bandwidth available is W hertz? So, there is an answer to this. So, what you need to do is, if you could avoid the constraint of 0 ISI, that means in the previous case we said that is the limit if you have 0 ISI as the constraint. So, if we reduce the constraint or relax the constraint that we do not want 0 ISI, there is a possible answer. So, then you could be imagining that we could remove that constraint and we could go ahead and achieve very fast signaling. But the problem is there is a limit to the amount of complexity that you can handle when you would like to cancel inter-symbol interference. So, at most 2 or 3 symbols interfering is a manageable complexity. Of course, things have become better these days, but this complexity that we are talking about is forcibly introduced by us and not by the channel. So, what we must be aware of, that there will be additional inter-symbol interference because of the channel, and we are introducing something more to it. So, we would like to restrict the amount of inter-symbol interference that we can allow in a controlled manner, and we get into the regime of controlled inter-symbol interference. We achieve this kind of a communication system by means of partial response signaling, and we had stated earlier the definition of partial response signaling, which we will revisit once again in the current context. So, given a bandwidth W, the maximum 2 W signals per second is for 0 ISI, which we have stated. For practical filters, this situation is less efficient. So, the different approach that we can use is to let the symbol transmission rate be 1 by 2 W by relaxing the 0 ISI condition and allow a certain amount of inter-symbol interference. So, 0 ISI would mean that x n t is equal to 0 for all n not equal to 0. That means, at all positions you are going to get a 0 crossing except at 0, right. So, controlled would allow at least one additional non-zero value in x and t. So, what it means is that instead of having all zeros, can we have a situation where there is a non-zero signal over here, or maybe a non-zero signal at some other point, right. Only one is the thing that we are trying to introduce over here. So, why? What would we get? We are going to get a symbol duration which is 2t, that means longer, and hence we are restricting ourselves to a bandwidth which is much smaller than the Nyquist bandwidth, and the remaining bandwidth that we have could be allowed for the roll off. The problem is, you could say that you are signaling at a much slower rate 1 by 2 t, but then if we send a signal at 1 by t, what we get is inter-symbol interference, but since there is only 2 symbols interfering, we should be able to cancel, and that is what we are going to see in this part of the lecture. So, if we say that x n t is equal to 1 at n equals to 0 as well as n equals to 1. So, that means, instead of this we are trying for a situation where it is 1 over here and 1 over here, at all other places it is 0. So, it is right, at all other places it is 0. So, that is what we are planning to introduce. So, what we have is the class of duobinary signals, right. The duobinary signals that we have can be visually seen by the solid black curve as we have over here in this particular picture. So, I will cover up the rest of it to avoid confusion. So, what we see is that in this case we have a non-zero value at 0 as well as we have a non-zero value at t. However, at all other places there is 0 value, right. There is another signal which we will also describe simultaneously, is where it is non-zero at minus t and non-zero at t, but it is 0 over here. So, this also introduces 2 symbols with ISI, because here if I am sending a signal I am going to get ISI for this, here if I send a signal I am going to get ISI for the red one, right. So, that means it allows certain amount of ISI, but since you can see that the span of the signal is more than the earlier situation, the bandwidth requirement will be smaller, and smaller than the Nyquist for W0, and if that is satisfied, the excess bandwidth that we have up to Nyquist could be used for a smooth roll off, which we are going to see shortly. Thank you.